So hi, welcome to my talk, 10 things you should know about Profiler. I will try to teach you how to use Profiler, how to analyze the data, and some of the things that I learned in the past year. But first, let's say thank you to the sponsors and also to the organizers and to all of you for coming here year after year, because without your support, I wouldn't be able to sit here and speak in front of you, because otherwise I wouldn't be joining the conference. Because I don't have a company to pay for. So my name is Jakub. I'm a maintainer of the Profiler module and of the Pester module. I do this in the evenings in my free time. During the day, I work as a software engineer in Microsoft, developing .NET testing tools like Testing Platform, MS Test, VS Test, and so on. I don't represent Microsoft here. All opinions are mine. If you do like my open source contributions or my development, or your company is using the tools that I'm creating together with the rest of the contributors, please consider sponsoring me on GitHub, because that helps me create t-shirts for this conference, come here, and so on. So thing number one, Profiler is a free tool. It's a free tool that you can download right now by just writing install module Profiler inside of your command line. And you can become the go-to person for PowerShell performance in your team. You can be the best one that everyone goes to ask when there is a performance problem. So you can see right now it has like 11,000 downloads. Maybe we can hit 1 million next year. What do you think? No? Let's try it. It only takes one CI server that just downloads it repeatedly. Thing number two, Profiler doesn't export many commands, but of the commands that it exports, trace script is the most important one. It takes a script block, it instruments it, runs the code that's inside of the script block, and then it gives you an overview, saved in this example in the $trace variable. So let's see how that works. I will switch to my VS Code. Clean this up. And so here you can see I have trace script. I give it a script block, and you can put any kind of code inside of the script block. It will scan every single PowerShell thing that will be invoked from the script block, no matter if it's hidden in a module, 5 functions deep, it will see it. So unless it's in a different run space, but it's something that I'm trying to figure out. But if it's PowerShell code that's running underneath the script block, you will be able to measure it, and you will be able to get the results. So here, what the function does, we just write to the host and we sleep for 2024 milliseconds to be a little thematic with this conference. And when I run the code, it shows me a lot of pink output or purplish output. Then there is the output to the host. And only the output to the host is being written to the screen. If you output something without writing it directly to the host, then it won't be written, because then you are most likely just testing the speed of the host itself and not the speed of your own code. When the script block finishes running, we report how long time it took. So in this case, 2 seconds and 40 milliseconds. We got 4 events, then we process them, which is really fast because there is only 4 of them, and Profiler can handle like 5 million in less than a second. And then we get this progress, and you can see I already have a bunch of numbers here because I've been running some scripts before. And this progress is very useful when you are rerunning your code, because it always tracks how long it took and compares it with the previous one, and it gives like 6 or 7 results. So you can compare your progress. So here you can see we run for 22 milliseconds. Then I run a different script probably, and we run for 2 seconds. No, sorry. Here we run for 2 seconds. I run a different script, and we run for 0 milliseconds. And then we run for 2 seconds again. So this way you can compare your progress, and you ideally want to see green, 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 or orange, which is the same execution time, but you probably don't want to see red, 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 because then you're making your script slower and not faster. Then the last thing that's happening here, Profiler inspected how we called the code. So it sees this variable being assigned. And it tells us what exactly you need to do, and that's use this view, because that's the most important view, and we will look at it in the next slide. But if you forget to do it, like here, like what I do most often, I run the code, it's profiling my code for like 3 minutes, and then I don't have the result. So it recognizes that you did that, and it tells you, don't worry, use this get latest trace. What did I do? Get latest trace. And it has the trace saved inside of the module. So it's a little convenience function that you can use when you do a little bit of a small mistake. You can use it to retrieve your latest trace. Okay, let's fix that back. And, ooh, wrong thing. That's the demo. The next item that you should know about Profiler is the top 50 self-duration view. That's the most important, most useful view that we have in Profiler. And we have it here. So I run the same code as before. It measures the code, and then I inspect this view, trace, top 50 self-duration. If you had bigger screen than I do here, then you don't have this format table at all. It gives you all the default information, the self-percent, self-duration, percent duration, file, line, the module where the code is coming from, and also the function in which the code is, and of course the code itself. And it also has additional information that it doesn't show you, which is the path to the file, because that's usually too long to put in the table. But if you want to either write it as a list or automate opening some file, you can use the additional metadata on this object to navigate exactly to the line of code, which is offending and which is too slow. And so in this view, we can see in the self% that we spend almost 100% of the time that this script was executing in this line of code. Start sleep for 2 seconds, which is kind of obvious from this very simple script. But if this call was hiding some free modules down, or in a function that calls a function that calls a function, this way you can get the top offending line in the execution and find out what is being slow. And usually it takes like 5 or 10 lines of optimizing the code to get your script 50% faster. At least that's my experience. And so the self% and self-duration are representing the time that's being spent only on this line of code and not any code that this line of code called. So in this case, we are calling into the .NET, so we don't have any other PowerShell code running underneath it. So this represents the time, and those both times are the same. But if we would have some other PowerShell code running underneath it, and I will show that in this other example, the times would be different, because this self% self-duration, those are only the single line and nothing below it. The percent and duration is the line plus every other PowerShell code that we called from that line. So here we have a different function. It's called getUnicorn. It outputs some unicorns and some log messages, because in one talk that I saw recently, I learned that emojis are very important. You should also go see it. It's the one from Jaap and Justin on PowerShell Summit. And then we log the message. For some reason, we sleep for 100 milliseconds here. And then we trace script the call to getUnicorn. We look at the top 50 self-duration. And what we see is, again, start sleep is taking overwhelmingly the most time in the execution. But if we go down, down, down here, for example, to the log message, you can see that now the numbers are different. Here, the self% is 0.08, because this call to the function took almost nothing. But all the code that this function called took 98% of the execution time. And that's probably a lot for logging. And this is how I use this to find areas to optimize. So for example, here, if we order it by the duration, it's just a different view. Now I run it again. No. F8. Come on. There we have it. So this is the same view, but it's ordered by the duration, and you can see that it kind of reads how the script executes. So we have the entry point, get unicorn, that always takes 100% of the execution time. Then we go into the for each object, then we go into log message, and we can see 99% of the time was spent there. So it kind of spans out. You could also represent this as a flame graph, which is a functionality that we have in Profiler as well. And so this way, if the overhead is too scattered and on the top of the self duration, you only see like this is taking 1% or this is taking 0.5%, then maybe you want to go and you want to look at duration and find a bigger area that you want to optimize that might not be doing what you are expecting. Okay. Now, item number 4, we have top 50 self-memory. And so this is a new view that I've added in the past year to Profiler, and this measures the memory consumed by the execution. So we're not measuring just time, but now we also measure the memory. Let's see it in action. Stop. Go away. So here in my example, I'm using the kind of epitome of slow code in PowerShell, the example that you will probably see in every single PowerShell performance talk, which is the plus equals on arrays. And what people usually say is this is slow because you go and you copy the array for every single item in the array. And so it happens like this, like what I'm describing in this comment. We start with an empty array. We create an array that has capacity of 1 item because we want to put the 1 inside of it. We add 1 and we end up with this array. We iterate again. We want to add 2. So we create a new array. We copy 1 into it. We have 1 space left and we put 2 in it and we end up with this array. Then when we want to add 3, we again copy 1 and 2 into a new array that has capacity of 3 and we add 3 and we end up with this one. And so on and so forth until we reach an array that has 10,000 items. And now if we profile it with Profiler, we can see it runs for 1 second and something. Okay, 950 milliseconds. This laptop is surprisingly fast at doing this. I don't know why, but on my home computer that can do everything faster, this just runs for like 2 seconds. And then if we look at the view, we can see that 99% of the memory was spent in this line of code where we are adding the numbers, so copying the arrays and everything. And we allocated 1.5 gigabytes of memory, which is crazy. We can also see here in the self-GC, which is the garbage collections that happened for this line of code, we did 159 of them during the 1 second. And we hit this 10,000 times, so that's not that very interesting. And so you might go home or you might try it on your own computer and you might say, but I didn't see any peak of 1.5 gigabytes of memory in my task manager. So why is that? It's because the memory that I'm describing is a memory traffic and not what you would see in a task manager. So if you look at a task manager, you would see something like this. You allocated some 30 megabytes of memory from the OS, and then you operate within that range. And so it runs up, up, up. You're allocating some arrays because all of those are object arrays, so they're on the heap. Create new ones, new ones, new ones. Then the memory pressure becomes too big, and the garbage collection kicks in, and it starts cleaning up. That takes some small time. And the objects are freed, and you again allocate, 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 clean up, allocate, allocate, clean up. This is showing 3 times when that happens. You could see in the previous slide that what it was, 129 times, 159 times. We repeated this process. So within the 30 megabytes, we created a 1.5 gigabytes of memory traffic, and that's what Profiler measures. So this is what you would see in your normal task manager. and it doesn't look like anything serious. It's just 30 megabytes of memory. But this is what really kind of happens. So we're using a .NET counter that is just adding and adding and adding and never goes back when there is garbage collection. And there are multiple ways I could choose to represent this, but I chose this one because it is the most obvious once you understand it. It gives you the most information, and it also works very similarly to time because it always goes up rather than going down. And so in Profiler, we capture it like this. We go up, then garbage collection happens, and you can see it has no impact on the graph. And then we go up until we reach the 1.5 gigabytes of memory that we saw in the previous slide. So item number 5, you can use Profiler to make PowerShell better for everyone. And so this investigation of the plus equals that I just did prompted me to look into why there is 1.5 gigabytes of memory allocated, because that sounds like way too much. We can even try a small example. We take 1 to 10,000. We sum it up like this. So we get all the sizes of the arrays that we would get from 1 to 10,000. And that should be, no, just the immediate number. So it's this 5 million something, no, 50 million. And then we can take the sum, we multiply it by the size of the integer, which is 32 bytes, 32 bits, so 4 bytes. And then we can slash it by 1 megabyte. So this is how much memory traffic we would want to see, like 200 megabytes. Not 1.5 gigabytes. And so because this seemed like too much, I digged into it, created an issue on PowerShell, talked with Jordan and Seemingly Science, and they're investigating how to make this better. Because what's happening in the PowerShell language itself, rather than just copying this array for every number, this is the code that's in there, except for small additions that I did. So for every single item, this is what happens. And this is showing the last iteration when we are adding the 10,000th item into the collection. So we start by creating a list. And in .NET, the list by default has a capacity of 4 items, which is way less than 10,000. Then we start a for each, and we start adding the numbers that we had before, which is 1 to 9,099. And we add it into the list. But the list only has capacity of 4. So when we reach that, we have to grow. And that happens by doubling the size of the internal array of the list. So it goes to 8, then 16, then 32. And like this, it grows to 16,384 because that's the smallest size that can accommodate my 10,000 items. So for this single iteration that we repeat 10,000 times, we have to regrow the list 12 times. And then we add the last item, the 10,000th item. And then just for good measure, because we wanted an array, instead of having a list, we call this toArray, which internally takes the array and copies it one more time. So 4 times at least for a single array, we copy it. For the case where we have the 10,000 items, we copied 14 times, progressively bigger and bigger. And that's why you see this exponential growth in the slowness of this plus equals. This is all only because PowerShell is treating the collection as a collection of unknown type and unknown size. So what Jordan is now working on, the pull request will realize that this is an array, and it will realize the size of the array. So in the end, what will happen, we just create a new array that has bigger capacity, 10,000 items, we copy, and we're done. That takes a few milliseconds and not a second, doesn't have to regrow all the time. And so if you would want to optimize this in the meantime, this is the fastest way that you have in PowerShell to process 10,000 numbers, do some operation on them, and then assign them to a new array that has 10,000 items. Some people might think, but isn't that the generic list? And you would be right. That's also a great alternative. Create a new generic list, add the items in it, and you have it much faster, but not faster than this. We can test it. I actually have a demo somewhere in the extras, but I think, how are we doing on time? Oh, very fine. If I can switch to it. So here, plus equals alternatives. So here we have a demo where we measure the original approach. Then we measure the assignment from the for each to a variable. Then we try creating a new list, but we forgot to set the capacity. So we will regrow the list the same way I just shown. And then we set the capacity to 10,000 items because we know how many there will be. So we don't regrow the list. We just move from one list to the other. And so when I run it, we can see the results. And so here, this took 900 milliseconds, allocated 1.5 gigabytes of memory. This took 117 milliseconds and allocated 31 megabytes of memory. This took 186 milliseconds and allocated 36 gigabytes of memory. And this took 186 milliseconds and allocated 36 megabytes of memory. Did I say gigabytes here? I meant megabytes. Gigabytes, no. And so here you can see the difference, some 0.3 megabyte. That's the amount of memory that you saved by pre-allocating the list. And all the other stuff, all the other 36 megabytes almost, is just an overhead of PowerShell of trying to run the code that you wrote. So this one just benefits from having less syntax because this is a keyword. So by all means, go on and use the collections generic list. It has other advantages. You can create it in this place. You can move it to another place, continue adding things into it. It's just not the fastest way to do this action. But I think it's very reasonable because if your script is only slower by how much? 100 milliseconds or 50 milliseconds, it doesn't matter on 10,000 items in the end. Okay. Item number 6, we have hit column. And so when I use Profiler, I usually look at the self-duration view or the self-memory view to figure out what is the slowest. And then I use the other columns to kind of hint me at what the problem is. So for example, here I have a hit count of 10,000 and I know about my script that it's running 10,000 times. So I'm expecting to see something like 10,000 here in this hit count. But what if I see 30,000? What if I see 60,000? Then I'm probably calling the function from multiple places too many times. It's in some loop where it shouldn't be. It should move up from the loop. I can cache the data and so on. So that's the kind of optimizations I can kind of guess just by looking at the hit count. And every time when I see a read of a file and I see a big hit count, I'm immediately looking, can I move this file read outside of the loop? Can I cache the data? Are they changing that much that I cannot cache them? Do I have to really hit the file 30,000 times? So an optimization for this kind of stuff that you can detect with the hit count is to move the file reads outside of the loops if you can. Don't forget about the get content raw, because that's an operator that keeps the usefulness of the get content commandlet, but it increases the speed for a lot of the applications where you don't need every single line to go through. When you need just the whole content of the file, like you take a file, you pipe it into convert from JSON. In that case, there is no point in reading the file line by line. You can just read it as one single blob and just pipe it in, and it just makes it way faster. And if you can, cache your data. If you detect that this is the problem, cache the data in some variable. So if you want a good talk about this, some good examples that are more detailed, I had a talk on this in 2022 where I'm showing 5 or 7 techniques that I took to optimize Threads module. And it made the speed about 50% faster than it was before. Just waiting for this. Good. Do you have the picture? Perfect. So now we learned how to get some how to analyze the data. Now we get some data to analyze. So first thing that you can do if you're starting with Profiler, profile your profile script. Because that's the code that you might be running quite often. You open a new window, it's slowing you down, and you might get angry. You move to a slower computer or on a battery operated like this one. You start your window and it waits for 5 seconds, and you're thinking, what's going on? It's very easy to see what is going on when you profile it through Profiler. And so that should be this demo, hopefully. Yeah, I need to run this in a new window, as the comment says, because otherwise it locks up my VS Code. Yes, please paste it. So I'm starting a new PowerShell session. I'm telling it don't load the profile because I will do that myself. And I tell it don't exit because I want to inspect the trace variable. I run this, it imports my module, hopefully. Okay, so that took 3 seconds and a bit. And now I can look at why is it so slow. And I'm just going to look at the first line. So hopefully we hit the right one. We didn't. No. Let's see. What do we have? Trace, top, 50, self, duration. I probably want the second one. So that's going to be index 1. Yes, that's what I wanted to see. I don't know why Chocolatey was slow. Sponsor alert. So when I run this on my profile, what I noticed is that this function from zLocation, which is a small module that I'm using every day, which allows me to write like jpester, and it just jumps into the pester folder no matter where I am, depending on how often I go into the folder. It's a lifesaver for me. So when it imports, what it does, it calls this com object to figure out from the Windows Explorer what are the most accessed folders that I have. This frequently accessed stuff. And that itself takes, in this case, 239 milliseconds. I also saw it take up to 500 or 600 milliseconds. And those are folders that I don't care about in the command line at all. There's our my profile, documents, and so on. So I don't need this functionality at all. And so I just decided to create an issue. Actually, I went to the repo. There was already an issue. Someone was complaining about this. So I just created a version of the module that can skip this code, and hopefully it will be merged somewhere. But in my own profile, I just deleted it from the module because it's slow and I don't care about it. You can also see in this output that we have the path that's directly going to the file if you ever want it, the line, the module, the function. Profiler tells you exactly where the code is. And so profiling your profile, good way to start with Profiler itself. So optimization in this case is skip the code you don't need. And when I was preparing for this session, I deleted like 40, maybe 50 functions from my own profile that at one point I wrote and I thought, this is a good idea. I will use this every day. No. I never touch them again. I use like maybe 5. One of them is to open my Visual Studio Code and navigate to different folders, create them based on folders. But I had slew of other stuff that needed to go parse every time I was figuring out where some files are. It was all slow, and I just followed the top 50 self-duration, delete, and suddenly it was much faster. So this is a valid. Another thing that I also discovered is that when you import pester, the most offending line is checking if we are on the Windows Nano server, if someone still remembers it when it was a thing. So it's dead now for a few years, and we are still checking. Are we in Nano server? No, we're not. And that takes 100 milliseconds, I think. So delete the code that you don't need. You can also profile your prompt. I know that some of you have very fancy prompts that are showing where you are, what time is it, what's your name, and so on. Maybe you can try to profile it, or maybe you are a creator of a module that is doing this for other people. So maybe you want to be informed about how long this kind of stuff is taking. Another thing to profile is profiling your module import. And in this case, this is not my module, PowerShell YAML, but I went through the list of the most used modules on PS Gallery. Thanks for the suggestion, Robert. And I tried to import them and see what's going on. And so PowerShell YAML has like 40 million downloads. And I think it's important to optimize your module load because it gives better experience to the users. It multiplies basically by the number of users and by the number of usages. And usually the optimizations are quite easy and quite the same. So here, when I load PowerShell YAML, it tells me what? Something else than what I expect. Let's restart. Okay, come on. Are we going to see it? Yes. So I had to restart because before this talk, the font was too small and I had to rerun every single module. And here in the comment, you can see it would be better to run this in a new PowerShell session, because if you run it in the same session, stuff like this, add type, will only trigger once, and you usually only import the module into your session once. So it's better to start it in a new session, do the import, look at the measurement, rather than repeat it like I do here. I only do it like this because it would lock up my Visual Studio Code, and I was a little afraid of that. And so I import module PowerShell YAML. The top line is add type. And add type, if you don't know, you can take a C# code, you compile it through add type, it creates a DLL, imports it into the session, and then you can use it to dynamically create types. And it's a rather slow operation because you have to start the compiler, create the DLL, import it, and so on. And so it's better if you take this code and you move it into a DLL, you compile it before you ship the module, and then you ship the module with the DLL build. Admittedly, this is an optimization that has like a high barrier of entry. If you have a single type in your whole module and you don't know much about .NET, you don't want to be building for multiple TFMs because you want to be supporting PowerShell 5 and PowerShell 7, and in the past, you had to support other versions. This might be very difficult to do for just a single type. But if we scroll down, we can see that PowerShell YAML already has assemblies that they import. So they could just take this text, move it into the other type, and they would get 40% boost on their import. Actually, on my home computer and in the slide, you can see it took 70% of the import. I don't know why this computer is just so fast or slow. But that's one of the optimizations. Another optimization is that if you have a module that's bigger and that's consisted of multiple files, then you take all the files and you merge them into one file, because that makes the load way faster. We did this for Pester, and it took the import from 3 or 4 seconds to 1 second. And that's where we are trying to be, at less than 1 second import for Pester. Okay. Yeah, here it says 77% for the import.
DBA tools was equal, but we had way more time. But
Did you merge it? The comment was that DBA tools was bigger, slower for the import than that.
yeah, because we had so many more files, so merging made such even greater difference.
Mm-hmm. Okay, yeah. So the merging of DBA tools made even bigger difference than for Pester. Okay, we went through this. So optimization, pre-compile your code if you want. Right now, it's pretty easy. You only have PowerShell 5.1 to support and PowerShell 7. If you want to see the easiest way to do it, you can go to Pester. We are building in the most optimized way that we can, I think, at least for our shipment. So we have pretty easy way of doing this and merge your files into one. Item number 10. You can profile anything else that I didn't show. As long as it's PowerShell code, you can go and profile it. Also, if you look at my talk from previous years, you can see how you can profile even the .NET code that's below the PowerShell code. So you can find slowness even in there. And Profiler is just trying to support all of this because I use it for my investigations and I want you all to be able to do the same. You can profile your Pester tests. Pester and Profiler are good friends. The code coverage in Pester is actually built on Profiler and it can run inside of each other. We had to do a lot of tricks to enable it, but it can. Your most used function from your favorite module, you can go and profile it and you can create an issue for all the things that I shown you here that would be optimizations. I filed an issue on the repo, asked them and shared information how they can resolve it. Any code that imports or exports data is a great place where to start optimizing because they usually do loops and they usually do file reads and usually it's not very optimized. So you can just go to some report that you're producing at work and that's taking too much time and be the hero and optimize it and make it faster. Get a raise, you know? And in fact, any code that you can think of, you can profile, share what you found. Maybe there will be more things that I didn't know. That's definitely possible. So that's it. So summary, use Profiler to find slow code, be the go-to perf person on your team. Use the columns and the views that are not self-duration to hint you at the problem. For example, this code is being run too many times. This code is eating a lot of memory traffic and so on. And report the issues that you find to the respective owner. If there is a module, just write an issue on the repo. Maybe they will never solve it, but at least it will be for reference for other people who can then fork it, create a new version, and create a new module and publish it. For more things about PowerShell performance, there is a link in the slides that you will all get, which goes to my YouTube list of PowerShell-related performance talks from me and from other people as well. And that's it. We can go to Q&A now, if there are any questions. Yeah. Thank you. Okay, Mike is incoming.
Apparently I am Mike man.
Thank you, Rob. So actually 2 questions. The first one is, so in order to calculate the self percent and the percent in the grid view you're showing, I guess you already do need to track the call stacks of the... So basically, I think you need to keep track of the call stacks in order to be able to calculate this information. So it would naturally come pretty easy, I guess, to create a flame graph visualization of this output also, which is maybe easy on the eye for a lot of people.
Yes, that's almost how this all works. And you can even do flame graph right now with the speed scope output. So this would be this, and this would be what? Export path, I guess. How did I call it? ABC speed scope. So if we go here, come on. Okay, what was your next question? If this loads.
First of all, that's amazing if this is already in there. I didn't know that. And second thing is it possible to basically attach in production into a running system?
Attached to a running system.
Like a kernel tracer would be able to.
Probably not, because we need to run code in the process to patch the UI and instrument it.
But you can, in theory...
in theory, if you would attach a manage debugger to PowerShell profile, you would execute the .NET portion of the code that we have, but you would have to acquire a PowerShell place where to run the code from the UI. So in theory, maybe, but it really depends on what you want to do. Lot of the stuff you can also see just by attaching any debugger and like doing the .NET thing, but then you don't see the details. So if you have a good use case, maybe we can work on it, or maybe you can sum it up as an issue. Okay, this is probably... Oh my God. It was, right? Disconnect and connect. Then it will ask me for the password, and I will not type it in. Okay, yeah. To answer your question, you can use the speeds code output. I demoed it in one of the previous talks. There is an online tool where you load the JSON. It shows you all the breakdowns. I don't know if it will be very comfortable to view for your taste, but I use it like a breakdown. Usually when I optimize anything, I just go into the top 50 self-duration, optimize those lines, and I don't care about that much because a lot of the other stuff is just getting faster. So, but it's possible. It still doesn't work, so I don't know. Are there any other questions, please?
Speak now, no chance.
Okay, I will just show you 2 more demos. So we already went through the alternatives to plus equals. And I also recently added red message to the bottom of the output when there is an error on the top. So usually when I run the tracing, I do something like this on the bottom. I leave all the 50 items on the screen, and it just barely scrolls up on my screen so I can see all 50 lines, and then I can see like this output. So until recently, this red message wasn't here. It just said done error or just done. And I didn't know that there's any error. And so usually what I saw was a very short runtime, and I was surprised and so on. And I couldn't understand why without properly looking at the trace. And so if there is an error here, now you also get a red message on the bottom. It's a little convenience thing, but for me, it's very important to be able to know when there is an error. So that's one thing that's new. And then also because I wired up this into Pester to do the code coverage on all the tests that we have, even on the tests that are not written in Pester, that we write in our special other framework. We weren't realizing that at some point in the execution of the test, we are turning off the tracing and then we are losing a lot of data. So I added auto detection into the tracing. So here, for example, one way to break Profiler is to take every single breakpoint and remove it because we depend on the debugging features of PowerShell. And so I run the script, then I break Profiler on purpose, and Profiler sees it, recognizes that the line that turned off the tracing is not the right line, and tells me the trace was broken by exactly this line from this file on this line. So we have very easy time now in Pester, and you will have easy time in Profiler. If you see data that you're missing, or there's something that is not in the output that where it should be because you know there's a slow code, you will get an error. And because Pester code coverage is depending on this, you would get readings that are way smaller than you would normally see. So for me, for Pester, before doing this fix and before fixing the code that was breaking it, I saw like 3% coverage. Now we have the 85% coverage that we had before, or maybe 75, I don't know. And so again, you leverage this, the red message, you go up, and it says the trace was broken by exactly this line. Which brings me exactly on the time. So if there's any more questions, speak up now or talk to me in the outside, somewhere in the corridor. Also, if you're Pester fans and you would like a Pester t-shirt, and especially if you didn't get one before, then talk to me. I can hook you up. I have few of them, and I have even very big sizes nowadays. So thank you again.